Greetings GCSE chemists. In this video we're going to be covering all of topic 3 chemistry, and that is quantitative chemistry. So we'll be looking at the concept of relative molecular mass, molar mass, the mole, Avogadro's constant, reacting mass calculations, limiting reactants, so all of topic 3. And to go with this video, you'll be getting free, yes free, whole of topic 3 knowledge organizer and use them as flashcards. So all you need to do is click the link in the description and we'll send them over to you straight away. Oh, and one more thing. Don't forget to check out the GCSE My Resources, which is also somewhere in the description, absolutely free. So if you're struggling with quantitative chemistry, have a look. We've got step-by-step instructions explaining each part of this topic with practice questions and work solutions. So what are you waiting for?
Greetings GCSE chemists. Welcome to this video where we're going to be looking at all of topic 3 quantitative chemistry. So before we start a single calculation, we need to make sure that we can read chemical formulae correctly, because every calculation in this topic fundamentally starts here. If we can't do this, we can't do the calculations and things fall apart pretty quickly. So what we're going to do is we're going to convert these pictures, diagrams on this page into chemical formulae. So we're literally counting atoms. So let's have a look at the diagram on the top left. How many nitrogen atoms do we see? Well, these circles are representing atoms of specific elements with this element symbol inside. So I count 2 nitrogen atoms and notice that the nitrogen atoms are touching. They're chemically combined. They are joined together as a molecule. So how do we write 2 nitrogen atoms chemically combined as a molecule? Well, we don't write it as 2N because that means something totally different. 2N would be, if we convert that into a drawing, that's how it would look. You can see we have got 2 nitrogen atoms, but they're not chemically combined via a bond. So it's not that. So in chemistry, what we do, because they are touching, we write the element label or the element symbol and then put a 2 subscript. There we go. So this is the stable molecule, makes up 78% of the air we breathe, there or thereabouts. Okay, let's have a look at the one to the immediate right of N2. So let's have a look. Let's count some atoms first of all. So we've got N, which stands for nitrogen. I count 1 of them. I have H, which stands for hydrogen, and I have 3 of them. So I've counted the atoms. So how do I write the formula? Well, this hydrogen is touching the nitrogen atom, so is that one, and so is that one. So they're chemically bonded. So let's start writing this. Now I could do H3N, I guess. However, there is a convention in chemistry. Now the convention goes like this. The atom of which there is only 1, so we only have 1 nitrogen, that will come first. So the central atom is usually first in the chemical formulae. So this isn't H3N, this becomes NH3. So that is the convention, that the central atom usually comes first and hydrogen usually comes after the main atom, with water being an exception here. Okay, so just to reiterate, 1 nitrogen, I don't have to quote the 1, it's an invisible 1, it's implied, and 3 hydrogens, subscript 3, that there are 3 hydrogens connected to the nitrogen atom. And this molecule is called ammonia. Very important, you come across it quite a lot at GCSE chemistry and A-level, Haber process, etc, etc. Okay, so let's have a look at the next set of, I'm not going to call them molecules, I'm going to call them formula units here because these are ionic. Okay, more on that in a second. So let's write down the elements that we have. I've got iron, Fe, and I have sulfur, S. I've got 2 iron atoms and I have 3 sulfur atoms. So the formula here will be Fe2S3. So here comes another convention when we're looking at metals, because the iron is a metal. The metal is usually quoted first for the chemical formulae. So we have to write Fe subscript 2, S subscript 3. So the iron sulfide. Just going to put the name as well. This is iron And I should say iron 3 sulfide, actually. I should say iron 3 sulfide. But more on that in a different topic. Okay, let's have a look at the final compound or formula unit in question. Let's write down the elements that we have. I've got Zn, which stands for zinc. I've got S, which stands for sulfur. And I have O, which stands for oxygen. I've got one of those. I've got 1 sulfur. And I have 4 oxygen. So how are we going to convert that into the chemical formulae? Chemical formula, I should say. So the metal is quoted first, then the SO4 is strictly speaking 1 unit, which is the sulfate ion. So this becomes ZnSO4. Okay. Now, from the chemical formulae, let's count the number of atoms. Let's see if we can do it this way around. So, first of all, BaCl2. Let's write down the elements that we have. We've got barium and we've got chlorine. So, how many bariums do I have? Well, it's not 0, but there isn't a number there. So because there isn't a number there, that is implied that it is a 1. 1 barium. And then you have a look at the calcium. Did I just say calcium? The chlorine even. There we are. I've got 2 chlorides. So how do we convert this chemical formula into the number of atoms that we have in there? Now that 2 is only applying to, not the calciums by the way, the chlorines. That is only applying to the chlorines, okay? So we've got 1 barium and 2 chlorines. There we go. Let's have a look at the next one to the right. H2O. Let's write down the elements in question. So this is water. I'm also going to put the name for BaCl2 because naming is important. That is barium chloride. Cool. So moving on. I've got hydrogen and oxygen. I've got 2 hydrogens. The 2 is referring to the hydrogens. The element symbol is before the number. So the number refers to the element that precedes it, I guess. So I've got 2 hydrogens and 1 oxygen. This you could call hydrogen oxide, but we are going to call it water. It's water. Right. Next one, Li2CO3. So we've got 3 different elements here. I've got lithium, carbon, and oxygen. Let's count how many atoms of each I have. So the 2 is not referring to the carbon. It is referring to the element before it. So that is lithium. So I've got 2 of those. No number next to the carbon to the immediate right. So it's a 1. It's implied. And to the right of the oxygen label, there is a subscript 3, so that is telling us that there are 3 oxygens. And this is lithium carbonate. Okay, and the next one. So here we've got some brackets. So mixing things up a little bit, the brackets, what you can do is treat everything inside as 1 group, then multiply by the number outside of the brackets. So just like in maths, the 2 outside multiplies everything inside the brackets. So let's think about this. Right, calcium, finally get to calcium, I have 1 of them. Now the oxygen, before I multiply by the 2 on the outside, let's just count everything inside. I've got 1 oxygen and 1 hydrogen. However, I've got a multiplier outside of the bracket, so that's multiplying all of the elements inside the brackets as well. So that is going to be multiplied by the 2. Tell you what, let's just box it. That's a good way of doing it. So that is going to be multiplied by everything outside the bracket. So the 2, so I've got 2 oxygens. And multiply the hydrogen by 2 as well. Whoop. There we go. So I have 2 hydrogen as well. Sorted. Not so bad, really. So next we're going to be looking at a relative formula mass, but in topic 1 we encountered a relative atomic mass. Now, quick overview of relative atomic mass. We've got the definition here. More on this in topic 1. Have a look at my resources. Have a look at the topic 1 video where we go through this in a little bit more detail and we calculate relative atomic masses from the isotopic abundance and isotopic mass. Right, let's have a look at the definition. So this is the relative atomic mass of an element that we're looking at, and this is the weighted average mass of an atom of a particular element compared to 1/12 the mass of a carbon-12 isotope, which works out to about 1. Why not hydrogen? We change the convention. This is the definition. Now, like we said, details on determining or calculating the relative atomic mass can be found on the isotopes and relative atomic mass, my resources note, and the link will be somewhere. So click the link. So just as a reminder, this doesn't necessarily need to be a whole number, and it's not for chlorine 35.5. That one is the one that we use quite a lot. Okay. Also, where do we find the relative atomic mass? Out of the two numbers in the periodic table, it is usually, in fact almost always, the larger of the two, apart from the case of hydrogen, of course. So, the relative atomic mass is usually the one at the top. Doesn't have to be, but it's usually the larger number. In fact, always the larger number. Now, that will be the relative atomic mass, the sum of the masses of the isotopes, weighted average, etc., etc., and the smaller number is the atomic number, the number of protons. Okay, let's go. Now, relative molecular mass and a relative formula mass. Now, relative molecular masses are calculated as the sum of the relative atomic masses of the atoms in a molecule. So, for example, now it sounds complicated, it's not that bad, trust me. The formula for water is H2O. Now, we know from looking at the periodic table, hydrogen has a relative atomic mass of 1 and oxygen has a relative atomic mass of 16. So what is the relative molecular mass going to be for this molecule? Well, let's count atoms. It always comes back to this. So you can see that in this molecule, there are some sticks connecting the hydrogens to the oxygen. Those are my covalent bonds. I have 2 hydrogen atoms and 1 oxygen atom, and then to determine the relative molecular mass, what I need to do is multiply this by the mass of 1 atom. So that has a mass of 1 and that has a mass of 1. So I've got 2 hydrogen atoms, I multiply it by the mass of what one of them weighs, so I have a combined mass of 2 coming from 2 hydrogen atoms. Okay. In the case of oxygen, oxygen weighs 16. I only have 1 of them. That's how many atoms of oxygen I have. I multiply that by the mass of 1, which is 16. So 1 times 16 is 16. And then what I'm going to do is add these guys up. Let's add these up. So 2 plus 16 equals my relative molecular mass, which is 18. Now, relative molecular mass is given the symbol capital M and a lowercase r. And subscript r as well. So lowercase and subscript. So that's how we determine the relative molecular mass. Now, a related quantity is the relative formula mass. Now, this is effectively the same as the relative molecular mass, but it applies to giant structures, i.e. ionic compounds, where the units or the species don't exist as molecules. So I don't get molecules of sodium chloride, we call them formula units. So strictly speaking, we should call it the relative formula mass, but we normally just use MR ubiquitously. It's just used all the time. So the formula of sodium chloride is NaCl. Right, how are we going to do this then? How are we going to determine the relative formula mass of NaCl? Well, let's write down our elements in question. I've got sodium and I've got chlorine. I've got 1 of those and I've got 1 of those. Okay, well, relative atomic mass of sodium is 23, so I multiply that by 23. And the relative atomic mass of chlorine, taking into account the abundance and masses of all the isotopes present, gives me 35.5. So 1 lot of 35.5 is 35.5. And then what I do is I add these together to get 58.5 as the relative formula mass of sodium chloride. Lovely. let's get practicing. So let's have a look at the relative molecular masses of oxygen followed by chlorine. So the MR for O2. Now, O2 is a diatomic molecule. Let's have a look at what the relative atomic mass is. It's 16. So first of all, find that in your periodic table. It is not 8, it is 16. It is the larger number. Now, in O2, there are 2 oxygen atoms. There are 2 oxygen atoms. So the MR is going to be 2 multiplied by 16, which is the relative atomic mass, which equals 32. And note that there are no units here for a relative molecular mass or relative atomic mass, okay? No units, dimensionless. No units. Okay, let's have a look at Cl2. So first of all, identify where it is in the periodic table. It's a halogen. There we go. Then write the element symbol or ID. So chlorine is Cl. There are 2 of them in Cl2. There we go. So the MR of Cl2 is going to be 2 lots of 35.5, which is equal to 71. No units. Now, let's have a look at something a little bit harder, which is the relative formula mass. It's not harder because it's relative formula mass. These are just some trickier examples. It's effectively the same skill that we're practicing as MR. Right, and people will still refer to this as MR. It's often used interchangeably and sometimes in the wrong context, but that's not the scope of this video. Let's practice. So let's have a look at all the elements that we have. So I've got, now, 1 nitrogen to start. I'm looking at the brackets first, followed by 4 hydrogens. Now there is a 2 on the outside of the bracket. So that is multiplying everything inside the bracket. So I need to multiply the nitrogen by 2 and the hydrogen by 2 to give me 2 and 8. Right, there we go. Those are sorted. I've got 1 sulfur and I've got 4 oxygens. All right, let's put a little line, and now let's have a look at the, I'm just going to call it MR. Let's just call it the MR, because why not? Now the MR is going to be equal to 2 lots of nitrogen times the mass of 1, which is 14, plus 8 hydrogens times the mass of 1. It's going to give us 8, and then plus, even, 1 lot of sulfur, which is 32, plus 4 lots of oxygen, which is 16. So the MR is equal to 132. No units there. Not too bad, not too bad. Another way of doing this is, if you want an alternative, you could say the MR of just this section is 14 plus 4, which is 18, and then times it by 2, and then add your 32 and your 64 due to the 16, the 4 lots of 16. So if you want the full working, you should get 132 as well. It's an alternative way of doing it. Now, a trickier example. This is a trickier example. This is hydrated copper 2 sulfate for question 4. Now, the dot in the formula is not an error, it's not a typo, okay? This dot stands for water of crystallization. So it stands for water of crystallization. And what that really means is the water molecules are incorporated into the crystal structure of the solid. So if they're incorporated into the crystal structure of the solid, you've got to include them when you're calculating the MR. So forgetting the water of crystallization is a common error on this topic, okay? So it must be included in MR calculations. Okay, let's count atoms. So I've got 1 copper, I've got 1 sulfur, I have got 4 oxygens. Now, let's do that bit first. Let's actually do that bit first. So copper is equal to 63.5 in its relative atomic mass. Sulfur is 32, as we've seen before. Oxygen is 16. So 63.5, 32, 64. Let's add all of this up and see where it gets us. So 63.5 plus 32 plus 64 should get to 159.5. But at the moment, I haven't included the 5 water molecules that I have. So water, the MR of H2O is equal to 2 lots of hydrogen plus 1 lot of oxygen, which is 18. So what I can just do here is put 18 there. So to account for the water, what I need to do is multiply that by 5, because I have 5 water molecules within the crystal structure. So let's do that over here. So 1, 5, in fact, let's do the MR, is equal to 159.5 plus 5 lots of 18. So that should give me 249.5. No units. Let's move on. Hopefully we're getting the hang of this. Percentage by mass. Why do we even care about percentage by mass? Now, really, really important. Very useful to know if you're going to go on to do A-level. Can really help out in some tricky situations. Obviously, we need to know it for GCSE, because let's say you had some iron deficiency, for example, and your doctor prescribes you some iron tablets. Now, they usually contain iron 2 sulfate. So the doctor's going to give you a dose based on how much iron you need, not how much iron sulfate you need. So the manufacturer needs to know what percentage of the tablet's mass is actually due to the iron as opposed to the iron sulfate, so they can make each tablet contain the correct dosage. And that again is coming back to percentage by mass. So let's have a look at the formula first of all. So if you know the molecular formula of a compound, you can calculate the percentage by mass of each element in that compound from the following formula. So you take the relative atomic mass, so AR stands for the relative atomic mass of the element in question, and you multiply it by however many atoms of that element you have. So if you have, I don't know, a lithium carbonate, going back to a previous example, well, I've got lithium that has an AR of 7, and in lithium carbonate there are 2 lithium atoms, so I multiply it by 2 there. And then what I do is divide it by the MR of the compound. We know how to do that. We've been practicing this skill. So, yet again, we're just counting atoms. We multiply it by 100 to get it, or express it as a percentage. Let's have a look. Let's have a look at an example. In fact, lithium carbonate, there you go. Percentage by mass of a lithium in a lithium carbonate. Well, let's find lithium first of all. So lithium is over here. So the relative atomic mass of lithium is 7. I have 2 lithiums in there. So I need to find the percentage by mass of lithium in lithium carbonate. So I'm only looking for the lithium or the element in question and how many I have in the numerator. Okay. So then I need to divide that by the total. I need to divide that by the total MR. I need to divide that by the total MR of lithium carbonate. So let's have a look at doing that, and we'll do that in this box up here. So counting atoms, I have got 2 lithiums. Each lithium has a mass of 7, so 14 in total. Carbon, I have 1. 1 carbon weighs 12. And then oxygen, I have 3 of them, multiplied by 16. I believe that's 48. So what does that give me? That's 74, he says. 74, if my mental maths is correct. So this is going to be 14 over 74 multiplied by 100. So calculators, the ready 14 over 74 times 100, we should get 18.9%. Bingo. Done. Okay, so what we're saying here is if we had 100 grams of lithium carbonate, 18.9% of it would be due to lithium, or 18.9 grams would be due to lithium. Now that's also relevant in battery technology. Lithium is very energy dense, but quite light as well. If not quite, it's very light. So light and energy dense, woohoo, fantastic material for batteries and battery technology. Okay, question 2, percentage by mass of nitrogen this time in barium nitrate. Okay, we've got these pesky brackets to deal with, but no problem. Let's go. Let's start by counting atoms. We'll do it a different way this time. So let's start by writing down the elements we have. So barium, we have 1. Nitrogen inside the brackets, we have 1. And oxygen inside the brackets, we have 3. We've got a multiplier of 2 on the outside. So we multiply the nitrogen and the oxygen by the number that is outside of the brackets. So then what we're going to do is multiply these by the relative atomic masses. So barium is 137. Okay, nitrogen is 14. And oxygen is 16. So that's 137. That is equal to 28. And then what's 6 lots of 16? 96. So the total MR is, I should probably make that look more like a 7. And I should probably make that one look more like an 8. So apologies for my handwriting. Trying to go neatly. So we should get a total MR of 261. Now this is a really nice approach. Slow and steady wins the race sometimes, okay? So the percentage is going to be equal to, well, the total mass of nitrogen, which is 28, over 261 multiplied by 100. And what does that give us? 10.7%, and done. Now the bracket here is crucial. If you forget to multiply the nitrate group by 2, you're going to get an underestimated MR and the completely wrong answer. So I think this is a neat way of doing it. Count the atoms first, then you've got everything to just substitute into a formula, and that is relatively trivial then. Okay, so moving on, we're getting to everybody's favorite topic, and that is this concept of the mole. Now, let's just dispel with the elephant in the room. Let's get rid of this as being difficult. It is relatively tricky to get your head around, but let's see if we can conquer this in today's video. Now, a mole of substance. A mole of substance, let's get this down. A mole of substance is the amount of that substance, that contains Avogadro's number of stuff. Avogadro's number. Now I said stuff here, but you can call them units, elementary units. Let's call it stuff. Avogadro's number of stuff. Now, what does the stuff or the units actually refer to here? Well, stuff in this context means, or can be, this can be atoms. Oh. Now, stuff here can be the number of atoms, molecules, and formula units. So ions as well, formula units. And actually electrons. I mean, whatever. Etc, etc. Stuff is a good catch-all term here. Now, 1 mole of any element, has a mass in grams that is numerically equivalent to its relative atomic mass. Also important. Now, 1 mole of any element has a mass in grams, G, numerically equal to, say, its relative atomic mass. Its relative atomic mass, parentheses, AR. Okay. I think it's also important to say here, and we're going to practice this and drill this skill, 1 mole of any compound, has a mass in grams that is equivalent to its MR. So numerically equal to its relative molecular mass, MR. Now, let's have a look at this in a little bit more detail. Now, going back to this concept of a mole is just a number. It is a word that represents a number, just like a dozen is a word that represents a number, which means 12. Okay, let's write that down. The mole, or a mole, is just a word that represents a number, just like 1 dozen represents 12. Don't worry about baker's dozens and all of that stuff. Just like a gross means 144. Now, a mole represents a number. What number? A whopping number, and that is Avogadro's constant. So 1 mole is equal to Avogadro's number, and Avogadro's number is 6.02 times 10 to the 23 things, stuff, what have you, of whatever. But the point is, it's absolutely massive. Now, Avogadro's number is always equal to 6.02 times 10 to the 23 of whatever is being counted. Now, Avogadro's number has the symbol capital N, capital A, but the A is subscript, so N standing for number, A standing for Avogadro, or L. You might see both depending on how old the question is or whatever. I mean, probably thinking, I hope we're thinking, that why on earth is it this mega number? And the reason is atoms are unimaginably small and light. A single carbon atom has a mass of around 2 times 10 to the minus 23 grams. You can't weigh that on any balance. You can't even see it, right? But if you collect a mole of them, 6 times 10 to the 23 carbon atoms, well then collectively they have a mass that is equal to the relative atomic mass, which comes out around 12. Something you can weigh, pipette, mix together. And that is the point of the mole. It bridges the invisible world of atoms and molecules and makes them visible when we have so many of them. It lets chemists count particles by weighing them. Okay, so going back to this section, let's explore this in a little bit more detail. Very, very important to understand conceptually what's going on. So, 1 mole of carbon, say, 1 mole of carbon has a mass of 12 grams. But given that we have 1 mole of the stuff, given that we're talking about 1 mole, well, anytime I see the mole, I must be referring to Avogadro's number of particles here, carbon atoms. So 1 mole of carbon has a mass of 12 grams, and it must contain 6.02 times 10 to the 23 atoms in this case. Well, 1 mole of magnesium, 1 mole of magnesium, this has a mass of 24 grams. Okay, we still have 1 mole of the stuff. So if we still have 1 mole of the stuff, we must have exactly the same number of atoms, 6 times 10 to the 23. Same number of atoms, however, one is heavier. So completely different masses, but each sample contains exactly the same number of particles. So this equivalence that makes these calculations possible, right? And the reason for this is, now if we explore this in a bit more detail, well, a carbon atom has 6 protons and 6 neutrons. Well, what about an atom of magnesium? Well, that's got 12 protons and 12 neutrons. So we've literally doubled the mass. So if you double the mass, you're going from 12 to 24, and that works out, going from the microscopic to the macroscopic, something that we can weigh. Hopefully this is starting to make sense. Now, 1 mole of Fe, 1 mole of iron, for example. Mole of iron has a mass of 56 grams. Well, if it's 1 mole, I've still got the same number of particles, which is Avogadro's number. Now, let's have a look at carbon in a little bit more detail, okay? Let's have a look at carbon in a little bit more detail. So let's see if I can get rid of the. So let's say I had 2 moles. Let's say I had 2 moles of carbon. Well, what have we done? I've doubled the number of moles. Well, if I've doubled the number of moles, I've doubled the number of particles, so I'm going to have double the mass, right? So 2 moles of carbon atoms will have a mass of 24 grams, equivalent to magnesium, but double the number of particles this time. So if I double that, that's going to be around 12.04 times 10 to the 23. So this becomes 1.204 times 10 to the 24 atoms. Hopefully we're starting to put pieces together now. Now, we've looked at atoms mainly, but this also applies to molecules and formula units, right? So 1 mole of H2O, 1 mole of H2O molecules, they have a mass. So 1 mole of H2O molecules have a mass of 18 grams. Well, we have 1 mole of them, so we still have Avogadro's number of particles. So we still have 6.02 times 10 to the 23 molecules this time. So we're not counting atoms, we're counting molecules. 1 mole. 1 mole of NaCl units, formula units, have a mass of 58.5 grams. But given that we have 1 mole, we still have the same number, which is Avogadro's number. But this time we're not looking at molecules because we can't get molecules of sodium chloride. So we have that many formula units, Avogadro's number of formula units of sodium chloride. So that simply is what we're talking about when we're looking at moles. Now, I think it's worth talking about units here. It's definitely important, and there is some value in being precise about it, okay? So, MR itself, MR is dimensionless, no units. We've seen that. MR is a dimensionless quantity. It has no units because it's defined as the mass of a formula unit or molecule relative to 1/12 the mass of a carbon-12 isotope. And because it's a ratio, the units will cancel. Now, the MR of, let's say we're looking at the MR of H2O. The MR of H2O, as we've seen, is 18, but there aren't any units associated with it. However, there is a closely related quantity called the molar mass. Now, so I'm just going to put no unit. However, molar mass, which is a closely related quantity, does have units. Now, molar mass has the symbol. Molar mass has the symbol capital M, no R there, okay? So capital M, no R, subscript, tells you that we're now looking at something different, a different quantity, which is called the molar mass. And it does have units because it has units of, grams per mole. Now, molar mass tells you the mass of exactly 1 mole of stuff. So, molar mass tells you the mass of exactly 1 mole of stuff. And what that means, of a substance. Now, numerically, molar mass is going to be the same as MR, but the only difference here is that molar mass will have units of how many grams there are per 1 mole of stuff, right? So, what we're really doing here is that MR is a microscopic comparison, whereas molar mass is a measurable mass of 1 mole of stuff. Now, remember that connection. That 1 mole of any element has a mass in grams, which is numerically the same as its relative atomic mass, or 1 mole of any compound has a mass in grams, which is numerically the same as its MR. Okay, so you can see that here. Very, very important. Okay, and just to drill that, let's say I'm trying to determine the MR of carbon dioxide. So we've got 1 carbon there. Carbon has an atomic mass of 12 plus 2 oxygens, which is 16. And that is going to be 32, no units. However, the molar mass of CO2 is going to be the same. Whoop, that should be 44 even. Now, the molar mass of carbon dioxide is going to be exactly the same numerically. So same number. However, if I have 1 mole of carbon dioxide molecules, they will weigh 44 grams per 1 mole. If I have 2 moles, it weighs 88. And I'll have double the number of particles there. Now at GCSE, the distinction between MR and molar mass isn't formally assessed. But it's important. And in calculations, we'll normally treat MR as if it has the units of grams per mole. But it's worth knowing that technically they're different quantities, but with the same numbers. More important at A-level, but just thought to get that out of the way for this video as well. Let's see, more importantly, is how we treat it, how we apply this concept. Okay, so what actually links the number of moles, the mass, and we put here MR, but like we said, that should technically be the molar mass. So, this is the formula that we need to know. Number of moles equals the mass divided by the molar mass. I'm going to refer to it. I might even use MR interchangeably here. Okay, so now the number of moles has the unit MOL. So the number of moles has a unit MOL. Mass has the unit of grams in chemistry, and molar mass, as we've seen, has a unit grams per mole of stuff. Now you need to be able to rearrange it. So let's practice a little bit of rearranging. So here is the number of moles. Now, I'm also going to use symbols here as well. Number of moles has the symbol N. So the number of moles is equal to the mass over the molar mass. So if I want to rearrange this for the mass, if I want to rearrange this and make m the subject, what do I need to do? Well, I need to get rid of this pesky divides by the molar mass. So in order to do that, I need to undivide. So undoing that division is timesing by. So I need to times by the molar mass on both sides. So if I do that, these guys shall cancel, and I have successfully made m the subject. Now, if we go up here, mass equals the number of moles times the molar mass. Now, sometimes people conflate the units and the symbols here, but we often say mass equals Mr. Mole. Mr. Mole because they put MR there, and then they use the units for moles and say mass equals Mr. Mole. Whatever works for you, whatever works for you. If you like it, use it. Whatever works. Now, from the number of moles equals the mass over the molar mass. Now, if I want to make the molar mass the subject here, what do I need to do? Well, I need the molar mass to be on the top. I can't have it at the bottom. So what do I do? Let's multiply both sides by the molar mass. And if we multiply both sides by the molar mass, they will cancel out here. Done. However, my molar mass on the left-hand side isn't on its own. It's tied to this multiplied by mole. So what do I do to undo that multiplication by moles? I divide both sides by the number of moles. They cancel out here. So the molar mass is equal to the mass divided by the number of moles, which you shall find here. Now, if you don't like rearranging and you think it's absolutely awful, what you need to do is figure out a way to learn this. Now, often people will use an equation triangle. I would say try and understand the formulae or the formula first. Try not to rely too much on formula triangles, but to each their own. To each their own. Whatever works, that's what you must do. Okay. Let's use an equation triangle as well. Right. So we need our variables. So what we're going to have here is N, which is the number of moles. We've got the mass followed by the molar mass. So, how does this work? You cover up the variable you're interested in. If I'm interested in moles, then I do mass divided by the molar mass. And there you go. If I'm interested in the mass, well, mass equals Mr. Mole. We all know that. Done. Let's put this into practice. Let's go. So this time we are going from a mass to moles. So what are we given? Well, we're given the mass of zinc. So what I'm going to do is carefully write down my variable. So I'm given the mass of zinc. It's 65. Now I also need to know the MR, or the molar mass technically speaking, but let's not get too excited about that. So the molar mass of zinc is 65. That's given to me from the periodic table. So 65 grams of zinc. The MR is 65. So what is the number of moles? Well, the number of moles is equal to the mass divided by the MR. So 65 over 65 is equal to 1 mole. 6 times 10 to the 23 particles there. Now, let's have a look at B. B is slightly more difficult because this time the mass is given as a ton. Well, okay, I've been revising my chemistry. I know that mass in chemistry should be in grams. Well, a ton, 1 ton is equal to 1,000 kilograms, and we need to convert kilograms down into grams, so this is going to be equal to 1,000,000 grams. That kilo means times by 1,000 there. Okay, so I've got a mass of 1 million grams of KCl. Okay, this is an ionic compound with formula unit, but we can just use MR here for simplicity. Now, potassium has a mass of 39, relative atomic mass of 39. Chlorine has a relative atomic mass of 35.5. So the MR of KCl is going to be 74.5 grams per mole. I know it's MR and using units there, but let's move on. We've done that. So what is the number of moles going to be? The number of moles are going to be 1 times 10 to the 6 over 74.5. What does that give me? So we should get 13422.8 moles. That's a lot of moles. That's a lot of moles. It's a lot of particles. That is a hell of a lot of particles as well. Right. Let's go. The last one now. Cheeky little question here. Cheeky little question, just like B. They haven't quoted the mass in grams. What they've quoted the mass in is a milligrams, which is 1,000th of a gram. Which is 1,000th of a gram. So what we need to do is the mass is going to be equal to 15 divided by 1,000, which is equal to 0.015 grams. Okay. Now the MR for chromium nitrate, is 238. Let's show the working out here. So chromium equals 52. Now what I'm going to do up here is work out what nitrate is. So nitrate is 1 nitrogen plus 3 lots of oxygen. So nitrate as a group is 62, but I've got 3 of them, so I need to do 3 lots of 62. So that should give me 238 grams per mole. Okay, so then let's work out the number of moles. That's going to be equal to 0.015 over 238. So you should get 6.3 times 10 to the minus 5 mole. Now, if you've got a question like this where they haven't given you the mass in grams, you will get a unit conversion mark. So converting into grams, you will get a mark for that, okay? So yes, it's important to practice these skills. Good overlap with physics here as well. Okay, this time, from the number of moles, we've got to go and determine the mass of the following substances. All right, no dramas, let's go. So first of all, let's think about what version of the formula we need to use. So remember, mass equals Mr. Mole. I mean, I don't normally use that, but let's write that down. Mass equals the molar mass times the number of moles. That is the version of the formula that we need to use. Okay, so what do we know? We have got the number of moles. It's 4 mole. We've got the molar mass for Br2 if we look at the periodic table. So it's 80 multiplied by 2 to 160. So the mass is going to be equal to 160 times 4. So 16 times 2 is 32. So this should be 64. Put the 0 on. Done. Let's move on. 4b. Same equation that we're going to use right at the top. Mass equals molar mass times the number of moles. But this time, the only difficult bit I would say is not necessarily use of the formula. That's relatively trivial. It's the fact that the MR itself is a bit tricky to calculate. Well, not tricky. We've got brackets, but we've seen this before. What we're going to do is let's treat the bracket first. So let's figure out the MR of the ammonium section. Now, nitrogen is 14 plus hydrogen, which is 1, but I have 4 of them, so I've got 4 lots of 1. So that equals 18. So my MR is going to be 18 plus phosphorus, which is 31, plus 8, plus 4 lots of oxygen, which is 16. So the MR should be 149. Let's just double check. 64 plus 31 plus. Now, hopefully you've spotted the mistake. The mistake is that in my haste, I didn't multiply the ammonium bit by 3. So let's do that first. So this should be 18 times 3. Now we are in business, and now that looks better. So 4 lots of 16. Okay. 18 times 3 is 54, plus 31 and plus 64. We should get 149. Done. Okay. So then the mass is going to be equal to 1.5 times 10 to the minus 3 moles multiplied by 149. Should get 0.224. 0.224 grams. Okay, last one. So trickier again, but only because the MR is tricky, not because it's hard in and of itself. So let's go. Number of moles is 0.35. Put my units in. What are you doing, man? Okay, let's have a look at the MR. So magnesium is 24 plus 1 sulfur, which is 32, plus 4 lots of 16, which is 64, plus H2O, which is 18 as an entity, but I've got 7 of them. So that's plus 7 lots of 18. And let's go through. We should get 246. 246, and then my mass equals 0.35 multiplied by 246, and 86.1. Final answer. Right, moving on to the Avogadro constant. Let's go. Moving on now, but related, we're going to be looking at the Avogadro constant in a little bit more detail. And these questions are really there to build your understanding of what Avogadro's constant actually means before we start using it numerically with atoms. Now, the logic in each case is identical. Total mass, number of particles, mass of one particle. Let's have a look at a non-chemistry example, but is related. Now, 1 dozen tennis balls. Well, anytime I see 1 dozen, it's a bit like seeing 1 mole, right? So dozen refers to a specific number. So dozen refers to 12. So in processing this, I'm thinking, okay, so 1 dozen equals, so that's the word for a different number. So 1 dozen is specifically talking about 12 tennis balls. That's how we're interpreting that, okay? So 12 tennis balls have a combined mass of that. Let's write that down. 552.36 grams. Now, my task is to calculate or determine the mass of 1 tennis ball, giving my answer to 3 sig figs. Okay, so how do I go from 12 tennis balls to 1 tennis ball? Okay, let's figure this out. What do I have to do to go from 12 to 1 in terms of multiplying or dividing? Well, I could just divide 12 by itself, right? 12 divided by 12 gives me 1. And whatever I do on one side, I do to the other. So what I'm really doing here is scaling down. So then if I scale the other side by that factor, so scale down, 1 tennis ball is going to be equal to 552.36 divided by 12. So what does that actually give me? So let's put that as a question mark. So therefore the question mark is equal to 552.36 divided by 12. Should get 46.0 grams to 3 significant figures. So it's a bit like a mole, right? Because a dozen is a bit like saying, oh, one mole of stuff has a combined mass of whatever, a big number. However, 1 mole is specific in what number that refers to. So 1 mole is a big number, whereas 1 dozen here is a manageable number. Let's call it 12. So if I wanted to work out the mass of 1 tennis ball or 1 atom, it's the same logic, right? So let's have a look at B. 3 dozen squash balls. Well, 3 dozen. Well, we know a dozen equals 12. We know a dozen equals 12. If I have 3 dozen, I've got 3 lots of 12, so that's equal to 36. So what we're saying here is that 36 squash balls have a combined mass of 108.30 grams. It's like saying 3 moles weighs whatever it weighs. So how do I get the mass of 1 ball? What do I have to do? Well, it's just scale factors, right? So let's divide 36 by 36 to get us 1 ball. So then what we're going to do, we're going to divide the right-hand side by 36 as well. So 108 divided by 36 should give me 3.01 grams exactly. Done. So this time we're moving away from a dozen, etc., etc., and we're moving to moles, okay? Now, same logic. 1 mole. 1 mole, we know what a mole equals. A mole refers to 6.02 times 10 to the 23 things. In this case, atoms, right? So that's the number that mole is referring to. So 1 mole is saying we have that many nitrogen atoms. And they all have a mass which is equal to the relative atomic mass that we see in the periodic table, which is 14. So all of that equals 14 grams. I've got to calculate the mass of 1 nitrogen atom, not a mole of nitrogen atoms. Because a mole weighs 14 grams, and that's that many atoms. 6 times 10 to the 23, Avogadro's number. I've literally got to determine the mass of 1. So how do I get the mass of 1 atom? Well, I need to divide that by itself to get the mass of 1 atom. So that's how I figure out the scale factor there. So I'm scaling down. I'm going to divide this by 6.02 times 10 to the 23 to give me the mass of 1 atom. Okay, whatever I do on one side, I do on the other. So I need to divide 14 by Avogadro's number. So what is 14 divided by Avogadro's number? It's a very small number, as we'd expect. So it's 2.33 times 10 to the minus 23 grams. That's how much 1 nitrogen atom weighs. Well, how much do a mole of atoms weigh? Well, we just multiply that. We just multiply that by Avogadro's number, because Avogadro's number is what a mole is referring to. So you scale that up by Avogadro's number, scale that side up by Avogadro's number, and voila, sorted. Right, let's have a look at D. Now this is a follow-up, it's a really good follow-up question, okay? So this time, anytime I see the word mole, I put in Avogadro's number. But this time I've got 4 moles. So what could I do? I mean, let's be specific actually. So that gives me 2.408. So what it really does is I have this many atoms in 4 moles. So I have that many lead atoms. And they have a combined mass of 824.8 grams. I need to calculate the mass of one lead atom. Okay, not 4 moles, because this is 4 moles. That's how many atoms 4 moles is equivalent to. So 4 moles of atoms weigh this much, 824.8, which is measurable, right? However, I'm after the mass of exactly 1. So what do I need to do? To go from that many to 1, I just divide the left-hand side by itself, which is that. There we go. And that takes us to 1 atom, and whatever I do on the left-hand side, I do on the right-hand side. So then on the right-hand side, I also divide by that huge number. So what do we get? So 824 divided by 2.408 times 10 to the 24. We should get 3.43. 3.43 times 10 to the minus 22 grams for 1 lead atom. Now, these answers are really illustrating exactly why we need the mole. Individual atoms are so light that working directly with the masses of 1 atom would be meaningless. Okay, we're just going to get this down. So individual atoms are so light, it would be tedious and meaningless working with individual masses. So instead, we work in moles. So packets of Avogadro's number, because that gives us something meaningful, something we can actually measure and use. Lovely. Moving on now, and this all links back to this concept of the mole. So we're looking at balanced chemical equations and molar ratios. Now, this is a bit like a recipe list, ingredients, okay? So a balanced chemical equation tells us 2 things: which substances are involved in the reaction and how much of each thing is reacting. What it really is telling us the exact ratio of moles in which my ingredients or substances react. Now, let's have a look at an example. So, our example here is C3H8, and let's call that propane. Now, in propane, what this is saying, the chemical equation is saying we have 1 lot of propane. By a lot here, I'm talking about 1 mole of propane. Now, if I have 1 mole of propane, that requires exactly 5 moles of oxygen to react. So, those large numbers in front of the formulae, or the formula, those are my coefficients, okay? So let's actually label these. These are my coefficients. So the large numbers written in front of each formula, these are the molar ratios or the coefficients. So we're going to call them coefficients. Coefficient, and these are the molar ratios. These are the molar ratios. So 1 mole of propane, C3H8, requires 5 moles of oxygen to react, and in doing so produces 3 moles of carbon dioxide and 4 moles of water. Produces 4 moles of water. Exactly. These are not approximates. This ratio is fixed by conservation of mass and conservation of atoms. Now, let's just see what would happen in instead of using 1 mole, let's say I used 2 moles of propane. Well, 1 mole requires 5 moles of oxygen, 3 moles of carbon dioxide produced, and 4 moles of water. So if I use 2 moles of propane, I'm scaling up by a factor of 2, right? Well, I have to scale everything else up by a factor of 2, otherwise I'm going to get the wrong outcome. I'm going to get the wrong dish. I'm not going to use the correct recipe. So that means 10 moles, 6 moles, and 8 moles. So hopefully we're seeing the connection here with the number of moles and chemical equations. Let's have a look at this in a little bit more detail. So if I used 4 moles, this time I'm scaling everything up by 4. So what we're going to do is 1 mole, 5 moles, produces 3 moles, and produces 4 moles. Let's just work out what those scale factors are. This time I'm timesing everything by 4. Okay, well, let's have a look at the one below. To go from 1 to 8, I need to multiply by 8, and I need to multiply everything by 8. I need to multiply everything by 8 in the case of B. Okay, C is a little bit more interesting. Because I've actually scaled down. I haven't scaled up, I've scaled down. So how are we going to scale down? Let's have a look. So let's go from 1, but this time we have a smaller number of moles. So how do we go from 1 to 0.25? Well, when scaling down to go from 1 mole, in this case, to 0.25 moles, how can we actually do this? Well, all we're doing here is timesing by 0.25, right? And timesing by 0.25 is the same as timesing by 1/4, which is the same as dividing by 4. Right, so you can times by 0.25, or you can just divide all of them by 4, whatever you like. So if you divide 1 by 4, you get 0.25. 5 divided by 4, or times by 0.25, you get 1.25. If you don't believe me, let's have a go. So 3 times 0.25, 3 times 1/4 does give us 0.75. 4 times 0.25 is going to give us 1 happy days. It all works out. That's what it means. And it's a bit like cooking, right? It's a bit like cooking. Let's say I have a strict recipe to make a curry sauce. Why not? It's the nation's national dish. So let's say I'm using 2 onions plus 1 garlic plus 1 chili, etc., etc. It's going to make a banging sauce. That's the base. I'm not including the spices here, etc., etc. But let's say that's the base for 1 banging sauce. Now, if I have to scale up to still get the banging sauce, what I need to do is, let's say more people are coming for dinner. I have to double the quantity. So that would be 4 onions, 2 garlics, 2 chili, 2 lots of sauce to accommodate. Well, if I'm cooking for fewer people, I have to scale it down, just like our chemical equations. Now, the recipe is fixed by conservation of mass, conservation of atoms. Here, this cooking recipe is fixed in order to get me a banging sauce. Any variation of these ingredients, what I start with, isn't going to give me the same sauce. It's fixed, just like in chemistry. Okay, let's have a deep dive into this. So let's have a look at the chemical reaction in question. So I've got calcium plus oxygen to make calcium oxide. But have a look at the coefficients, the molar ratios. What this is saying is 2 moles of calcium, 2 moles of calcium react with 1 mole of oxygen. There is an imaginary 1 there. There is a 1 there. We just don't put it there. So don't think there isn't a number there. There is. Forms 2 moles of calcium oxide. Okay, Just looking at the coefficients there to get those numbers. All right. Now, in this little table, what we are told is we're either scaling up or scaling down. Let's have a look. So, let's start from the chemical equation. 2 moles of calcium requires 1 mole of O2 to react, forming 2 moles of calcium oxide. But what have we literally done? What have we literally done going from 2 to 8? We've times that by 4. Well, if we times that by 4, we times that by 4 to give us 4 moles, and we times that one by 4 to give us 8 moles. And another way of looking at it is, well, look, 2 moles of calcium requires half the number of moles of oxygen to react. So if I have 8 moles of calcium to start with, half the number of moles of oxygen need to react. So we could have just divided that one by 2, starting from the relationship of the number of moles of calcium to molecular oxygen. Let's do B that way. Let's do B that way. Just a different take on it, okay? So I could just scale them all up. Let's just do a different take. So starting from this number of moles, we know that the calcium number of moles needs to be 2 times bigger. Well, I'm just going to multiply that by 2. That is the ratio between the O2 and the calcium. If I have whatever the number of moles of oxygen is, the number of moles of calcium needs to be 2 times more. So this is going to be 6 moles. Okay. And then going in the other direction, the molar ratio between oxygen and calcium oxide is 1 to 2. So the calcium oxide also needs to be 2 times more. So 6 moles. All right. So that's another way of doing it. So what we could do is this. Does the scaling also give us the same result? I mean, it will, but let's just double check. Let's convince ourselves. Okay. To go from 1 to 3, we're timesing by 3. So, does 2 times 3 give us 6? Yeah. Does 2 times 3 give us 6? Yeah. Same thing. Same thing. Okay. Last one. So this time we are going from 2 moles to 0.2. So we're not scaling up, we're scaling down. Okay. So how do we go from 2 moles to 0.2 moles? Okay. What is going on here? So the way to work out the scale factor is, for scaling down, we are going to take the smaller number, which is 0.2. We're going to divide it by the larger number, which is 2. And that's going to give us our scaling factor. So 0.2 divided by 2 is equal to 0.1. So 2 times 0.1 gives us 0.2. And hey presto. So what we're going to do here is multiply this by, keep it in black so it's consistent, times that by 0.1, times that by 0.1. So that should be equal to 0.1 mole. And then times that by 0.1. Whoop. And that will also give us 0.2 moles, which should be the same as the calcium number of moles. And that's it. That is it. A harder example, but we've got this. So this time we're taking iron, reacting it with chlorine to make iron 3 chloride. What does the chemical equation actually mean? Well, we know this. We've got 2 moles of iron reacting with 3 moles of Cl2 to form 2 moles of iron 3 chloride. Okay, now what is going to happen if I have 20 moles? If I have 20 moles of iron, can I just work out the scale factor? Yes, I can. To go from 2 to 20, how do I work out the scale factor? Well, you take the larger number, which is 20, divided by the smaller number, which is 2, over here. I shall put a box around it. There we go. A lovely jubbly. Right. And that gives me a scale factor of 10. So, I multiply this by 10. So 3 times 10 is going to give me 30 moles needed. I multiply that by 10, and that is going to give me 20 moles needed. Okay, lovely stuff. Now, there is a little shortcut we can take. Don't rely on the shortcut. Always make sure you do it the long way first, so you know what you're doing. Then the shortcut can be used, okay? You got to know why you're doing the shortcut in the first place. So what I could do is let's have a look at the ratio of chlorine to iron. It's 2 to 3. So what we're really saying here is that this 30 moles, or this 3, in fact, let's do it up here actually. Let's do it up here. So 2 lots of Fe plus 3Cl2 goes to this. Okay, what we're really saying then, if I have 3 lots of that, 3 moles of that, this number needs to be not scaled up, but scaled down, right? Well, how do we scale down? Well, it's sometimes easier going in this direction. I know it sounds ridiculous, but to go from 3 to 2, well, what you're starting with, where you want to end up is the 2. So you are going to do 2 divided by 3, where you end up what you're starting with. So 2 divided by 3, that is our scaling down factor, okay? So if we do 3 times 2 over 3, does that take us to 6? Yes, it does. Sorry, does that take us to 2 for the iron? Yes, it does. Absolutely. If you don't believe me, 3 multiplied by 2 over 3. The 3's cancel out. You are simply left with 2. Or 6 over 3, which is 2. So, sorted. Now, another way of thinking about this is, well, let's say I didn't know that direction. In fact, let's start from scale. Let's actually try the scaling up version. Let's try the scaling up version. So let's say I had 4 moles of this. Now, the iron to chlorine ratio is 2 to 3. So how do I scale up going from 2 to 3? Well, that would be multiplying by 3 over 2. So dividing by this coefficient and multiplying by the coefficient that you're ending at. So timesing by 3 over 2 is the same as timesing by 1 over 5. So timesing by 1.5 even. So 4 multiplied by 3 over 2 is equal to 12 over 2, which is equal to 6. Now, does that work? We're multiplying that by 2 and we're multiplying that by 2. Yeah, happy days. It's just scaling up, right? So there we go. We should see the connections here. We're still going to just do these by the scaling up method like we've been doing. All right. So how have we then gone in B from 3 to 18? So 3 multiplied by some number, which works out to be 18. Well, that is going to be 6. So I'm multiplying that by 6. Okay, well, if I'm multiplying that by 6, I'm multiplying this by 6. So 6 lots of 2 are 12 mole. And then I'm multiplying this by 6 as well, because I'm scaling up. 6 lots of 2 are 12 mole. Happy days. Let's move on to the last one. Okay, the last one may look tricky. It may look tricky, okay? So what we're going to do, just get rid of green in terms of more space. Okay. We are going from 3 to 0.18. Okay, what is this factor? I'm scaling down here. So 0.18 divided by 3 gives me my scale factor. So it gives me a factor of 0.06. Okay, so we're going to times that by 0.06. Okay, well, if I'm timesing that by 0.06, I need to multiply this by 0.06 as well. So what's 0.06 times 2 should be 0.12 mol. And same thing here, I'm going to multiply that by 0.06, 0.12 mol. And you can check, you can also check, is this 0.18, is it 1.5 times bigger? Is it 1.5 times bigger than 0.12? How can we check that? How can we check that? Look at the ratio between these guys. It's 2 to 3. So 0.12 times by 3 divided by 2. Let's have a look. So that should be 0.36 divided by 2 gives me 0.18. Happy days. It all works out. Lovely stuff. Cool. Great. So this is really fundamental to reacting masses calculations. All right, let's get a bit of a wiggle on. So what we're doing in my scale factor here is to go from 1 to 6 is 6. So I'm going to multiply all of these by 6. So 6 4s are going to be 24 mol. That's going to be 6 mol, and that is going to be 24 mol. Sorted. Okay, the next one. So what are we doing for the sodium? We're going from 4 to 8. So we're scaling up by a factor of 2. So everything else needs to be scaled up by a factor of 2. So that's going to be 2 mol. That's going to be 2 mol. And that is going to be 8 mol. Okay, last one. What are we doing then? I can rub some of this out. Okay. We are going from 1 mol this time. We're going from 1 mol of titanium tetrachloride to 0.04 moles. Okay, how am I going to work out what this factor is? So all I'm doing is 0.04 over 1, and that gives me what I'm multiplying by to scale down. So it's 0.04. Was that 400ths? Lovely. So times that by 0.04. Happy days. Okay, times that by 0.04. Now, you could do it without a calculator, because 4 4s are 16. 16 over 100 is 0.16 mol. Cool, and we can do the remaining ones, titanium and sodium chloride as well. So that is going to be 0.04, and that is going to be 0.16 mol. And there we go. Job is done. Not too shabby. Let's go. Okay, so hopefully we're happy with each individual skill when it comes to reacting mass calculations. The big boy of questions could be like a 5-marker, maybe a bit less, but there could be lots of things going on. What you have to do, this is a multi-step process. You're putting together all the skills we learnt in one hit. That's why some people find it difficult, or at least challenging. I'm going to use the word challenging. It's not beyond us. So let's have a look at a reacting mass calculation. Now, we have to determine, that just means work out the mass of water produced. So we're trying to work out the mass of water produced when 8 grams of methane, CH4, is combusted, reacted in excess oxygen. And they've given us a balanced chemical equation. This isn't a balancing equations question. They will give you that more often than not. And how do we read this? This is saying that 1 mole of CH4 is reacting with 2 moles of oxygen, making 1 mole of CO2 and 2 moles of H2O. Okay. So what we're going to do is we're going to tabulate this. So we've got the chemical equation going from left to right, because in the Western world we read from left to right. And then we're going to start with ratio. Right. Ratio. So the ratio, where do we get the molar ratios, or the stoichiometric ratio, which is sometimes called? Well, we get it from the chemical equation. That's the ingredient list and the recipe, right? So CH4 is my ingredient. How much of it is my molar ratio? That is my recipe. How much am I adding? So I got 1 to 2. It's going to give me 1 lot of that to 2. So there's my ratio. Okay, so then let's have a look at the masses. Do I know any masses? Well, yeah, from the question, I know that I have 8 grams of methane. So I find methane, CH4. And in my table, my second row is labeled mass. So what I'm going to do here is put 8 grams for methane. Then, do I know the mass of O2? No, but I'm not interested in it, so all good. I don't need to know the mass of CO2, but I am interested in the mass of water. I'm definitely interested in that. So what I'm going to do is move that to here, because that is my unknown. That's what I have to work out. So let's leave that as my blank. That's what I'm trying to determine. So, do I know the MR of methane? No, but I know how to do it. So yes, let's do that. Carbon. I've got 1 carbon which weighs 12. Show this in your working out. And I have got 4 hydrogens. So 4 hydrogens, each hydrogen weighs 1. So the total MR is 16. By the way, that is 1 mark there. That is 1 mark. Okay, well, if I'm not interested in the oxygen or the CO2, I can just ignore those. Not part of the question. Don't do extra stuff. You're not going to get extra marks. So, what am I interested in? Well, we're going to go down the table. So always hit your table like this. Ratio R triple M. So ratio mass MR moles. Okay, well, if I know the mass of something, and the MR, I can determine the number of moles, remember? So, how do I do that? The number of moles is equal to the mass over the MR. So the number of moles is going to be equal to 8 over 16. Don't leave it as a fraction. That is going to be equal to 1/2. Let's call that 0.5 moles. That is another mark. 2 marks. Now, where do we go to next? Because my aim is to finish up here, right? I'm trying to work out the mass of water. Okay, great. So I know the MR of water because we practice it a lot, and you can just get it for free from the periodic table, right? So this is going to be 2 hydrogens. So that is going to be 2 times 1 plus 1 oxygen, which is going to be 1 times 16. So if you add that up, that is going to be equal to 18. Now, do not use the large numbers. Do not use the coefficients when determining the molar mass, because what we're really doing is determining the mass of 1 mole of stuff, not 2 moles of stuff, okay? So this is really the molar mass. That's why we had that bit in this video to talk about that. So do not multiply by coefficients to determine the MR or the molar mass. Do not do that. We're trying to work out the mass of 1 mole, not 2 moles in this case. So don't scale it up by 2, because that is mass of 2 moles, and you have to scale back down. Just don't do it. Don't do it. Right, where do we go to next? So got that bit, but I also need to know something else. I need to know the number of moles of water that I have, because we all know that mass equals Mr. Mole. So the mass is equal to the number of moles times the MR. So what are we going to do? How am I going to work this out? This is a bit puzzling. Isn't it puzzling? So let's have a look. There are multiple ways to do this, okay? There are multiple ways to do this. So let's have a look at the substances in question that I know about. So I know about the methane, and from the chemical equation, it's a 1:2 ratio, right? However, how many do you actually have? Well, you've got 0.5 moles. Okay, well, let's think about this. What have you done? You've scaled down. You've gone from 0.5 over 1. So that's just timesing by 0.5. Timesing by 0.5 is the same as dividing by 2, right? So we multiply that by 0.5. Well, if we multiply that one by 0.5, then how do we work out the number of moles of water? Well, we do the same thing, right? We're going to times that by 0.5 as well. So 2 times 0.5 or 2 divided by 2 is 1. So this should be equal to 1 mole. Double check. By the way, that is a mark. That is a mark. So you're using the chemical equation, and what you're doing here is, look, the ratio between these guys is 1 to 2. So whatever that number of moles is, so in this case 0.5, this has to be 2 times bigger. So 0.5 times 2 does give us 1, right? So what you could also do if you wanted to, you could do something like this, where you're multiplying it by 2, showing the examiner as well. And then how do you work out the mass of H2O? Well, the mass now is trivial because we've got the equation we need. It's the number of moles, which I have, which is 1, multiplied by 18. So my mass is equal to 18 grams. 1 mark there as well. So maybe a 3 marker. Maybe a 3 marker. In fact, I'd say 4 marker. 4 marker there as well. So mark coming in from using the stoichiometry or the molar ratios. Okay, let's up the ante. Let's go a little bit harder, but we've got this. It's the same thing over and over. It's the same procedure, okay? Always set it out in the same way. So, table. First of all, chemical equation. Ratio, mass, MR, mold. And by the way, there is a little symmetry to this. I guess, because if we're going in this direction, we're dividing the mass by the MR to give us the mold, and then once we have the mold of the substance that we need, have a look what's happening. In fact, let's change the color. It's a bit more striking. Okay, there we go. And going up in the other direction, if you have the mold and the MR to get the mass, you just multiply together. You multiply these. So there's this nice symmetry aspect to it, I guess. Right, let's go. Right, so we've got the balanced chemical equation. This actually links to chemistry of the atmosphere topic about the removal of ammonia from the atmosphere as oxygen starts, as the oxygen concentration increases, and that's how we end up with like 78% nitrogen, I think. Cool. So what are my ratios? My ratios are 4, 3, 2, 6. Okay, do I know any masses? Yeah, let's have a look. So I'm trying, my job is to calculate the mass of O2. So this baby. So that is the mass of oxygen needed to react with 12.5 grams of ammonia. And it tells us what ammonia is. So this is NH3. So where it says NH3, put 12.5 grams. Okay, what is my MR for ammonia? Well, do not do this. Do not do 4 times. So do not use the coefficient. Don't do that. But 1 nitrogen is 14 plus 3 hydrogens is 17. Don't scale that up by a factor of 4. Do not use that when determining the MR or the molar mass, as I should probably say. Cool. So, if I have the mass and the MR of one substance, I can work out the number of moles, because the number of moles equals the mass over the MR. So the number of moles is going to be equal to 12.5 over 17. So the number of moles is 0.735 mole. Cool. So that's a good place to start. All right, so then how am I going to work out the number of moles of oxygen? Well, there are many ways to do this. So let's have a look. I need the number of moles of oxygen, right? So let's have a look. So 4 lots of NH3 to 3 lots of O2. So we can use this scaling method like we've done before. However, I've got 0.735 moles. So how do I work out that scaling factor? This is going to be 0.735 over 4. So what does that give us? 0.1838. Okay, well, let's do the same on this side. So that times 3 is going to give us the number of moles here, which is 0.5515 mole. Happy days. That is it. There is nothing more to it. So that is going to be 0.55 moles. So that's one way of doing it, okay? That is one way of doing it. Now, a variation on that theme is this. So imagine we didn't do it that way. Is there a shortcut we could use? Yes, there is, because we are scaling down, right? We're scaling down from 4, let's go for green, to 3. Okay, how do we scale down from 4 to 3? Well, we need to divide by 4 and times by 3, right? In fact, going vertically can be easier to see. So the number that we're trying to end up goes in the numerator. Divide by 4 times by 3. Yeah, that's it. That's another way of doing it, right? So I would say that's a nicer way of doing it, but whatever works. You get the same result, hopefully. So 0.735 times by 3 divided by 4, 0.5515. Okay, so let's get all of it in. Times by 3, divide by 4. Yeah, 0.5515 moles. What I'm doing here is, by the way, I'm leaving this whole number in the calculator, then timesing by and doing the ratios, then rounding up at the end, just in case yours looks slightly different to mine. Cool, so I've got the number of moles. Where do I go to next? I then need the MR of O2. So the MR of O2 is 2 times 16, which is equal to 32. Don't times by 3. The MR is related to the molar mass, so 1 mole of stuff, so 1 mole of oxygen molecules is 32. If I times by 3, I'm working out 3 moles. So then to work out the mass equals MR times the moles, MR times N. So this is going to be, do I have N? Yes. Do I have the MR? Yes. To get the mass, I'm going to multiply them together. It's going to be around 16, isn't it? You get 17.6. 17.6 grams. Happy days. By the way, MR marks, probably 1 MR mark. A mark here for determining the number of moles, timesing by the, or dividing by 4 and timesing by 3, or using the molar ratios in some fashion. You could have done it the long way like we did at the top. And then what we're doing is getting a final mark. So probably a 4 marker there. Probably another 4 marker. Okay. Now the next one. I'm going to say it's challenging. It's challenging. It's not hard. It's challenging. Let's have a look. Now, it's a slightly different technique. It's a slightly different technique to this type of question. So what's going on? In the words of Marvin Gaye. Right, we've got a 6.5 gram sample of hydrated sodium carbonate. Hydrated, just like it means in common language, common speak, common parlance, is that there is some water in here. We know that this is water crystallization. So what I'm going to do, where it says sodium carbonate and hydrated with this water crystallization, I'm going to put 6.50 grams because I have the mass from the question, right? And then it loses 3 grams of water when heated to constant mass. Okay, well, do I know the mass of water lost? Yes, because 3 grams of water is lost. When it is heated to constant mass, what you do is you put it in a crucible, heat it, keep on heating it until the mass stays constant. That means all that water has been removed. Okay, so I know the mass of water. it's 3 grams. Now, based on conservation of mass must be conserved in a chemical reaction. So if I start with 6.5 grams, how can I just end up with 3? Where did the rest of the mass go? Well, the rest of the mass must be due to the sodium carbonate. So, how do we work out the mass of sodium carbonate? That is going to be the initial mass, take away 3.0. So my mass of sodium carbonate is 3.50 grams. Okay, what you have to check is, does the mass of sodium carbonate, when I add the mass of water, equal the mass I start with? Yes, it does. Lovely. All right, so I've got masses. I don't have MR. Now, I don't have MR for my hydrated sodium carbonate because I don't know how many water crystallizations I have. I have to work out N. Okay. However, what info do I know? Well, I do know the MR of dehydrated and hydrosodium carbonate. So let's work that out. So I've got 2 sodiums. So 2 lots of 23. Plus 1 carbon. Plus 3 lots of 16. What does that give me? What is the MR? So 46 plus 12 plus 48 should get 106 as my MR. Cool. Well, I also can work out the MR of water, right? I can also work out the MR of water. Because, remember, you don't take into account the N's, so that's not a hindrance here. So that is going to be 2 lots of 1 plus 1 lot of 16. My MR here of water is 18. Now, do I have masses and MRs? Yaha. If I have masses and MRs, what quantity can I work out? I know we're all shouting moles. Okay, because the number of moles is equal to the mass over the MR. Well, we are in business. So let's work out the number of moles of each. So the number of moles of sodium carbonate is going to be 3.5 over 106. And the number of moles of water is going to be 3 over 18. Okay, what do we get? What's 3.5? Should get 0.033. And what's 3 over 18? That is 0.167 mole. Okay, we are getting there. Now, just put some boxes, make it nice and neat as well. Hey, right, there we go. Now, I've got the number of moles, but I don't have the coefficients. But the coefficients are the simplest ratio of moles, right? So, the coefficients are the molar ratios, the simplest ratio of moles. So, let's have a look. Well, I have got, let's see if I can take this there, that many moles of sodium carbonate. I've got that many moles of water. Well then, how do I get these coefficients? Well, these coefficients are simply the ratio of moles, right? So let's take the simplest ratio of moles that we have calculated. So to get the simplest ratio, divide by the smallest number of moles. So divide by the number of moles of sodium carbonate. So that will give us 1 mole, or 1 lot, 2 5.05, but that is close enough to 5, so n is equal to, so what we're going to do is replace that n there, n is equal to 5. And there you go, tricky question. Okay, moving on to limiting reactants. This is more challenging than straightforward reacting mass calculations. This is more tricky. There are more parts to this. But let's take it back to something that we're familiar with. Now, everybody is familiar with burgers. Whatever the meat or substance is of your choice. It could be a bean burger. It could be a beef burger. It could be whatever. It could be chickpea and beetroot. Whatever you like. There are some patties there and there are some buns. Patties and buns, okay, in this little picture. So, these are my buns and these are my patties. Okay, so buns and burger patties, okay? Now, the question is, what limits how many assembled burgers I can make? Well, okay, well, if we put this patty into that bun, I'm going to make one burger, right? And I do the same thing for this patty as well. I will make another burger. However, have a look. I've got some bun left over, but not enough patties. So what limits how many assembled burgers I can make? Well, it's not the buns. The buns are actually in excess. So think about the terminology here. So the buns are in excess. I have plenty of those. So the buns are in excess. They are in excess. However, the patties limit how many burgers we can make. Okay. Now, this idea of something being in excess, one thing being in excess, and another thing being limiting is really, really important, okay? This links very nicely with chemistry because in some chemical reactions, we want some reactants or reagents to be in excess, and then the other thing reacting by definition be the substance which is limiting that reaction, and that determines how much product we make, okay? So let's say our product here is 2 burgers. Well, the limiting reactant has determined that, right? Let's go. Get thee gone. Okay. Going back to molar ratios. It's all to do with this, really. It's all to do with this, okay? Now, here we've got a chemical equation. Calcium oxide plus water make calcium hydroxide. Let's call that lime water because it is. Now, we can see from the molar ratio, it's 1 to 1 to 1. Okay, there's a 1, 1, 1 molar ratio. So then, how do we figure out what's limiting and what is in excess? Okay, now when the chemical equation is 1 to 1 to 1, there are only 1s in the molar ratio, then it's actually quite easy because the larger value is the species or the substance which is in excess. Because what we're really saying here is that 1 mole of calcium oxide needs 1 mole of water to make 1 mole of calcium hydroxide, right? So, if we times that by 2, then what we're saying here is that 2 moles of calcium oxide need 2 moles of H2O to react. But actually, I have got 3 moles of H2O. I've got more moles than I actually need. So therefore, this is going to be the reactant which is in excess. Now, you could do it a different way. Because you could say the flip side of that, right? So what you could say is this. Let's times that one by 3. And then remember, you have to scale up in the same way. So if we do 1 times 3, that gets us to 3 moles. So for every 3 moles of water, we need 3 moles of calcium oxide. But we don't have 3 moles of calcium oxide. We've got 2. We've got less than we need. Given that we've got less than we need, the calcium oxide has to be the limiting reactant, right? So this is the way to think about it. So when it's 1 to 1 to 1, easy. This is the limiting reactant. That determines how many moles we make. So once we've identified what the limiting reactant is, this is going to be 2 moles of calcium hydroxide. Okay, let's have a look at B. So let's scale up. So we're timesing that by 12 to go from 1 mole. Okay, so that means we also have to times the number of moles of H2O by 12, right? So if we times that by 12, this is what we need to react. So we need 12 moles to react with 12 moles calcium oxide. However, we don't have 12 moles of calcium oxide. We have fewer moles than we need, right? So we need 12 moles. We don't have 12. We've got less than 12. Given that we have less than 12, what does that mean about the water? Well, the water is the limiting reactant. This is the limiting reactant. Okay, given that that is the limiting reactant, what we can effectively do is ignore the excess, which is the way to think about it, okay? So we can just times that by 8, because the limiting reactant determines the scale factor, because that determines how much product we make. So we times that by 8, so that equals 8 mole. Done. Okay, let's have a look at the last one. So similar thing, we are timesing that by 0.4. So if we times that by 0.4, let's times this by 0.4. So if we have 0.4 moles of calcium oxide, we also need 0.4 moles of water to react. But this is the number of moles that we are actually given. So 0.6 is bigger than the 0.4 that we need. So we've got more moles of water than we actually need. Therefore, the water is in excess. I'm just going to put excess here, okay? So we've got more moles than we actually need. So the smaller number, when it's a 1-to-1-to-1, is always going to be the limiting reactant. Okay, so we know what the limiting reactant is. Let's label it LR. So then what we're going to do is times that by the limiting reactant scale factor. So 1 times 0.4 is going to be 0.4 moles produced. Okay, so let's multiply that, the 2 to 4, by 2, because that's my CL factor there, okay? So what we're saying is for 4 moles of iron, if I multiply the 3 by 2 as well, then that means I need 6 moles of Cl2. But I don't have 6 moles of Cl2. In fact, I have less than that. So I can't use that 2 times scale factor here. So then we can determine that the Cl2 is a limiting reactant. So I'm just going to label this as the LR, because I've got fewer moles than needed, right? I need 6 moles for every 4 moles to react, but I've got less than that for the chlorine, right? So this is definitely the limiting reactant. This is definitely the limiting reactant. Okay, so then what I could do is this. How do we go from 3 to 4? How do we go from 3 to 4? Well, I'm dividing by 3 and timesing by 4. That's how I'm scaling up. For the limiting reactant, I'm going to do the same thing for the product, because that is determined by the limiting reactant and not the reactant which is in excess. So 2 times 4 is 8. What is 8 over 3? It gives me 2.67 moles. Sorted. Good. Okay, let's go. Let's have another look. All right. Let's go for a different color. So let's have a look at B. To go from 2 to 12, I'm multiplying by 6. All right then. So for every 12 moles, what we're going to do is multiply the 3 by 6 as well, by the same scaling factor. So 6 3s. So that is 6, 12, 18. Okay. So for 12 moles of iron, I need 18 moles of chlorine. But I don't have 18 moles of chlorine because I only have 15. So that is the limiting reactant again. Okay, cool. Once I've identified the limiting reactant, what do I need to do? I need to work out the actual scale factor of 3 to 15. So that is going to be 5. So I'm scaling by 5 there. So what do I need to do? I also need to scale this up by 5. So 2 lots of 5, that is going to be 10 moles. And done. Quite a nice way of doing it, I think. Okay, let's have a look at the last one. So the last one is going to be... Let's work out that. Pick one of them. It doesn't really matter which one you pick. So that is scaled up in C by 5. Okay. I'm just going to rub some of these out for clarity. Okay, so that is being scaled by 5. So then let's scale this by 5. Okay, so 3 times 5 is 15 moles, but this time I've got 20 moles of chlorine, so I've got more than I need. So this is now in excess. So this becomes my limiting reactant, and I've already worked out the scale factor for the limiting reactant. It's times 5. So I go to the product, and I also times it by the scale factor for the limiting reactant. This also becomes 2 times 5, which is equal to 10. So we are sorted. Done. Right, let's go. Last one before we get on to some juicier calculations. Let's have a look. Right, 2 to 1 to 2. That is the ratio. So 2 to 1 to 2. So I'm just going to write this down. 2 moles of calcium need 1 mole of O2 to make 2 moles of calcium oxide. Okay, so let's pick the easy numbers. So let's figure that one out first. So we are scaling that one by 3. Let's scale this by 3. So if I scale that by 3, well, that is saying I need 6 moles of calcium for every 3 moles of oxygen. I don't have 6 moles of calcium. I've got 3 moles of calcium. So I don't have enough. So this is my limiting reactant. Now I need to work out the scale factor for my limiting reactant, right? So let's work out my scale factor for my limiting reactant. Because remember, the limiting reactant determines the amount of product that we make. So how do we go from 2 to 3? Well, I divide by 2 and I times by 3, times by 1.5, right? Same thing here. So times by 3, divide by 2, and that is also going to give me 3 mole. Done. Let's have a look at the next one, B. So just going to rub out most of this. So let's just pick this for no particular rhyme or reason. We are going from 2 to 12, so let's scale that up by 6. So we're also going to scale this up by 6. So 1 mole of oxygen, if we scale up by 6, we need 6 moles. So for my 12 moles of calcium, I need 6 moles of O2. But I don't have 6 moles of O2, I've only got 2 moles. So therefore, I've got fewer moles. This is my limiting reactant. Okay, so I've worked out the limiting reactant. Where do I go to next? Let's work out the scale factor. To go from 1 mole of O2 to 2, that is a scale factor of 2. Let's apply that same scale factor for the limiting reactant to the product. So 2 times 2 is going to give me 4 moles. Okay, hopefully this is going in. Right, finally, C. Let's pick one. Let's pick one. So what have we done? We have divided by 2 and times by 1. So we're timesing by a half here, okay? We're timesing by a half. Okay, well, if we also times by a half, by the way, that is the limiting reactant. That is the limiting reactant. I can't remember because I rubbed it out. No, it would make sense that that is the limiting reactant. Cool. All right. There we go. All right. So let's scale that by timesing by a half. If we times that by a half, we are expecting 0.5 moles of O2. But I don't have 0.5 moles of O2. I have got 0.4 moles of O2. So I've got fewer moles than I need. So this is my limiting reactant. This is my limiting reactant. Okay, now we've established that. We now need to work out the scale factor for the limiting reactant. So we're going from 1 mole to 0.4. That is times 0.4. Well, 2 times 0.4 is 4/10. So that becomes 8/10, which is 0.8 moles. And happy days, the job is done. Okay, cool. That's the theory. That's the theory behind limiting reactants. Let's have a look at some juicier questions. Final table to process, and then we're going to have a look at some actual questions. All right, we've got a table full of moles. We need to work out what the limiting reactant is. How do we do that? Let's scale. So we're going to times that by 1.5. Okay, so we're timesing by 3 dividing by 2. Okay, so let's do the same thing here. Let's times by 3, divide by 2. So 3 times 3 is 9, divided by 2 is 4.5. Okay, so for 1.5 moles of N2, I need 4.5 moles of H2. Okay, great. I don't have 4.5 moles of H2. I have less than that. I have 3 moles. 3 is less than 4.5, so H2 is going to be my limiting reactant. Okay, let's work out what my limiting reactant is. I've just done that. This is my limiting reactant. Okay, now let's work out the scale factor for the limiting reactant, because that is the scale factor that determines how much the product scales by, because the product is determined by the limiting reactant. So we're timesing that by 1. We're timesing this by 1. So this is going to be 2 moles of ammonia. And done. That's it. Right, same thing for B. Let's scale. So that's being times by itself. Let's do the same thing. Let's times that by 1. Okay, so for 1 mole of N2, I would need 3 moles of H2, but I don't have 3 moles of H2. I don't have 3 moles of H2, so I have less than that. Given that I have less than that, as 1.8 is less than 3, this is my limiting reactant again. What do? Now I work out the scale factor for the limiting. Bit of a weird one. So that's going to be 1.8 over 3. What does that give us? 0.6. Okay, works out quite nicely. So then what do? I apply that scale factor to the ammonia. So that is going to be, what's 2 times 6/10? 1.2 mol. Looks about right. It looks about right. Okay, cool. So then finally, let's go. For C, let's scale that one up by 3. We also have to scale up this one by 3. Okay, so for 3 moles of nitrogen, I would need 9 moles of H2. But I don't have 9 moles. I've got 10 moles. So 10 is bigger than 9. So that means this is going to be my reactant in excess. This is going to be my reactant, which is limiting. We've already worked out the scale factor for the limiting reactant. So what we are going to do is times this one by 3 also, and 3 times 2 is equal to 6 moles. And done. All right. Limiting reactants. So this is more akin to the actual type of problem you would get. So we've got the balanced chemical equation. How do I know it's a limiting reactant problem? Well, I've got 2 masses, because I've got the mass of lead oxide reacting with the mass of carbon. Okay, cool. So step number 1. what we are going to do is work out the number of moles. So you could do it in table form. I'll also show you a different way of doing it. So step number 1, let's work out the number of moles of PbO. All right, so this is going to be 10 grams divided by, so what's lead? I think it's 207. So remember, the formula that we need to use is the mass over MR. So this is going to be, in fact, let's work out my MR. So the MR of PbO is equal to 207 plus 16, which is equal to, what do we think? What is that equal to? Trying to do 223. Yep, 223 looks about right. Okay, so 10 over 223, it gives me what? So that gives me 0.044. That does not look like a 0. 0.04484 mole. Okay, so I've got the number of moles of PbO. Okay, where do I go to next? Now let's work out the number of moles of carbon. So the number of moles of carbon is equal to 3 over 12. So what's that, a quarter, he says? So 0.25. Sorted. Okay, now I have to work out which one is the limiting reactant. Okay, what we're going to do is this time we're going to use the stoichiometry, okay? So then, let's pick the carbon number, pick either one, either the lead oxide one or the carbon one, it doesn't matter. And we can do it from, we're going to do it 2 ways. We're going to do method number 1. Okay, so 2 PbO, 2 carbon. So 0.04484 to 0.25 mole. Okay. Right, so what we're going to do, let's pick the carbon one and scale. So we're timesing that by 0.25, and let's also times that by 0.25, right? So what's 2 times 0.25? So that is going to be 0.5 mole. That is going to be 0.5 moles. Okay. Well, I clearly don't have 0.5 moles of lead oxide needed for my 0.25 moles of carbon reacting. I've got way less because 0.04484 is way less than the 0.5 moles needed. Okay, what does that mean? Well, we've figured out what the limiting reactant is. This is the limiting reactant. Okay, given that that is the limiting reactant, I can get rid of the carbon. So let's get rid of the E. You can go away. Right. Okay. Done with you. Don't need you anymore. Okay. Now let's have a look at the lead that I need. Now I need to calculate the mass of lead formed. Okay, so I've figured out what the limiting reactant is. So now I'm going to put here the ratio of lead that I make. It's 2 to 2. Okay, well, that one, to go from 2 to there, well, I don't even have to do that step. Given that the lead oxide and lead ratio should be the same, well, this is simply going to be 0.04484 moles from the limiting reactant, which determines the amount of product. But let's do it properly. All right. So what is that scaling factor? It's going to be 0.04484 over 2. So it's 0.02242 times by, and I'm going to times by that on the other side as well. And you should see that you'll get exactly the same number of moles. So that's the sort of long way round of doing it, okay? And on the next question, we'll do it a different way. Oh, that should be 4484. So I've got the number of moles of lead from the limiting reactant. So then what do I do next? So number of moles of lead is going to be 0.04484 moles. And then step number 4, the mass of lead is going to be the number of moles multiplied by the mass of lead, which is 207. And we should get 9.28 grams exactly. Cool. So that's the sort of longer way of doing it, but it's complete. It's complete. There we go. Right. Put some boxes there as well. And happy days. Okay. Next question. Next question. So a different way of doing it. Okay. So step 1, you're given 2 masses. We need to work out the number of moles of each. So let's work out the number of moles of each. Okay, so let's do it as a modified sort of table. So via the chemical equation, we've got 2 moles of iron reacting with 3 lots of Cl2. So I've got 15 grams of Fe and 50 grams of Cl2. So let's work out the number of moles. Divide that by 56. Divide that by 71. So my moles equal, if the calculator decides to work, there we go. 15 over 56 is 0.267. 2679 mole, and then 50 over 71 is 0.704 mole. Okay, which of these is the limiting reactant? What I'm going to do is highlight one of them. Let's highlight this number. Doesn't matter which one, pick one of them. And then the ratio between iron and chlorine is 2:3. So that is saying that the number of moles of chlorine needs to be 1.5 times more than the number of moles of iron, right? So to do that, to work that out, we're going to times by 3 and divide by 2. So timesing by 1.5. So that is telling us that we need 0.4018 moles of Cl2 to react. But 0.704 is what we have, and that is greater than the 0.4018 moles we need. So the chlorine is in excess, and the iron, therefore, is limiting. Okay, so then I need to work out the mass of iron chloride produced. So what's going to determine the number of moles of iron chloride? It's going to be the limiting reactant. It's a 2:2 ratio, so this number of moles is going to be the same. And then, once I've got that, to get the mass of FeCl3, this is going to be 0.2679 multiplied by 162.5. What do we get? Should get 43.5, bang on. Done. Okay, our last subtopic, which is all to do with concentration. Don't mean you're thinking really hard about something, but how much stuff there is in a given volume. That's what we're talking about when we're discussing concentration. Now, for combined higher, we only need to look at concentration in terms of how much stuff there is in terms of mass per decimeter cubed, okay? So this is a mass concentration. So we're just going to get this down. So concentration is how much stuff there is in a given volume. By stuff, what I'm really saying is how much solute there is dissolved in a given volume of solution. So a concentrated solution has a large amount of solute per unit volume, whereas dilute has very little solute per unit volume. Okay. Now, the unit, as we've discussed here, is grams per decimeter cubed, and 1 gram per decimeter cubed is equal to 1 litre, which is equal to 1,000 centimeters cubed. Okay. So, just a quick point. So this is mass concentration. Mass concentration is equal to the mass in grams divided by the volume in decimeters cubed. Okay, now we've already looked at some unit conversions for masses and stuff when we're looking at reacting masses, but for volume, to go from centimeters cubed to decimeters cubed, have a look, you are dividing by 1,000. And you've got an equation triangle here to help you as well. Let's go. So question number 1. I've got to determine the concentration from the following. So what I'm going to do is write down what I know. So I don't know the concentration, but I know the mass. It's 200 grams. And I have the volume already in decimeters cubed. Huzzah! Okay, so concentration is going to be 200. In fact, it's going to be the mass divided by the volume. So 200 divided by 10 is going to be 20 grams every decimeter cubed. Type 1 question. Right. Different version. I've got to calculate the mass this time. Okay, so what I'm going to do is I'm thinking that concentration is mass divided by volume. So to work out mass is going to be concentration times volume. Let's double check. Mass, if I cover that up, is concentration times volume. Yeah. Okay, so now let's write down what I know. So I know the volume because it's 6 decimeters cubed. I know the concentration. It's 20 grams per decimeter cubed. So what I'm going to do in step 3 is just plug these in. So it's going to be 20 times 6. So that's going to be, what, 120, is it? He says 120 grams of solute. Of KBr, that is. Cool. All right. Last question. Calculate the volume in centimeters cubed. Good question. Of salt solution with the concentration and mass known. All right, cool. So let's write down the equation. Concentration is mass over volume. So the volume is going to be the mass over the concentration. So let's write down what we know. I know a mass, it's 8 grams. And I also know the concentration is 40 grams per dm cubed. Okay, per dm cubed. Okay, so then my volume is going to be 8 over 40. So what does 8 over 40 give me? 0.2 grams. Grams? Right. That has units of grams. This is units of grams per decimeter cubed. So the grams cancel out. This is going to be equal to 0.2 decimeters cubed. Now, it actually says to calculate the volume in centimeters cubed. Okay, so how am I going to calculate the volume in centimeters cubed? Well, centimeters cubed to decimeters cubed is divide by 1,000. So to go the opposite way, that is going to be times by 1,000. So the volume is going to be 0.2 times 1,000. This is going to be 200 centimeters cubed. Ta-ta.
So if you found this video useful, Don't forget to like, comment and subscribe. Tell us what content you want and we shall deliver.